You hear the phrase, the nearest star, and something inside your mind quietly relaxes. Because nearest sounds manageable. It sounds like the next step after the moon, after Mars, after the slow expansion of human footprints across the solar system. And when astronomers announced in 2016 that a rocky planet roughly the mass of Earth was orbiting Proxima Centauri inside the habitable zone, it felt less like a discovery and more like an invitation, as if the universe had placed a second shoreline just beyond the horizon and waited to see whether you would notice it. And I want you to pay attention to how seductive that idea is. Because the moment you hear Earth-sized, habitable zone, closest star, your brain quietly stitches together a story where the journey is difficult but inevitable. The same story we told ourselves about crossing oceans, reaching the poles, stepping onto the moon. And it all sounds reasonable until you slow down and ask what closest actually means in physics instead of language. Proxima Centauri sits 24 light years away. And that number looks polite, almost modest. The decimal point makes it feel like something measured carefully, something contained, but a light year is not a human unit. It is the distance light travels in 1 year, moving at nearly 300 kilometers per second. And once you translate that into something physical, the illusion begins to fracture. Because 24 light years is about 40 trillion kilometers, which is not just far. It is far in a way that does not scale with anything you have experienced. Not with driving across a country, not with flying across an ocean, not even with sending probes to the outer planets. And the danger here is that the word nearest tricks you into thinking this is the beginning of a staircase, when in reality it is the edge of a cliff. I want you to imagine shrinking the entire solar system down to something you can hold in your mind. Shrink the sun to the size of a basketball. Earth becomes a grain of sand orbiting a few dozen meters away. Jupiter is a marble down the street. Neptune sits roughly a kilometer out. And everything humanity has ever explored fits inside that small neighborhood. Every spacecraft, every mission, every triumph, all of it still within walking distance. And now you ask where Proxima Centauri would be on that same scale, and the answer is uncomfortable, because the nearest star is not across the city, not across the country, but thousands of kilometers away, another ball on another continent. And suddenly the word nearest stops sounding comforting and starts sounding like a joke. The universe is playing on your intuition. The discovery of Proxima b amplified that illusion, because now the destination was not just a star, but a world. And human thinking is shaped by worlds, by coastlines, by mountains, by places you can stand. So the mind automatically fills in a narrative where the hardest part is deciding to go. But physics does not care about narratives. It only cares about distance and energy and time. And the distance between naming a place and reaching it is where the romance quietly dissolves into arithmetic. Light leaving Proxima b right now takes over 4 years to reach you, which means every telescope image you see is already history. And if you tried to send anything back, even a signal, you are committing to conversations that unfold slower than human memory. And that alone should give you pause, because exploration in the solar system still feels connected. You send a command, you wait minutes or hours. Something responds, but at interstellar distances, even thought begins to stretch thin. Cause and effect separate, and the idea of going there starts to feel less like travel and more like exile. The strange thing is that none of this makes the discovery less exciting. It actually makes it more honest, because Proxima b is real, a rocky world in the habitable zone of the nearest star. And that combination is scientifically extraordinary. But the moment you call it reachable, you step away from physics and into wishful thinking. And the uncomfortable truth is that the closest destination beyond our sun already lives at a scale where human ambition begins to lose its grip, where the gap between seeing and touching becomes so large that even the word journey starts to feel misleading. Because what you are really confronting is not distance as you know it, but distance as the universe defines it. When you first hear 24 light years, your mind tries to compress it into something familiar, something you can compare to a flight time, a long voyage, maybe even a difficult but achievable expedition. And the problem is not that you misunderstand the number. The problem is that your intuition quietly replaces it with something smaller. Because the human brain evolved to navigate forests and coastlines, not vacuum and relativity, and when numbers become too large, we don't really grasp them. We domesticate them. We pretend they belong to the same category as everything else we've crossed before. And that is where interstellar distance becomes deceptive, because 24 light years is not just far, it is far in a way that changes the rules entirely. 1 light year is about 46 Trillionen kilometers, which means Proxima Centauri sits roughly 40 trillion kilometers away. And those words still don't help much, because trillion is just another abstraction. So you reach for something more concrete. You ask how long it would take to get there using the fastest machines we've ever built. And that is where the scale begins to push back. Voyager 1. The most distant human-made object has been traveling since 1977, drifting outward at about 17 kilometers per second, which sounds impressive until you realize that at that speed, the journey to Proxima Centauri would take roughly 73,000 years. And that number does something strange to your sense of time. Because 73,000 years is not a long mission. It is longer than civilization itself, longer than agriculture, longer than writing, longer than cities. Which means if Voyager had been launched when humans first began painting caves, it would still not be halfway there. You might try to rescue the situation by choosing something faster. And the fastest spacecraft humans have ever built is the Parker Solar Probe, which briefly reaches nearly 190 kilometers per second as it dives close to the sun. And even at that extreme speed, the trip would still take around 700 years, which is shorter, but only in the mathematical sense, because 700 years is still longer than recorded history, longer than the pyramids, longer than the rise and fall of empires. And what this reveals is not just that the journey is long, but that the concept of travel itself begins to break down when durations exceed the lifespan of cultures. The deeper issue is that everything we have ever accomplished in space sits inside a tiny bubble compared to this distance. We've landed on the moon. St. Probus to Jupiter. Saturn, Neptune, even left the heliosphere. But all of those achievements occur within a region measured in tens or hundreds of astronomical units, while Proxima Centauri lies more than 268,000 astronomical units away. And the gap between those numbers is not incremental. It is a discontinuity, like stepping from a pond into an ocean without realizing the shoreline has vanished behind you. I sometimes think about this in terms of motion, because motion is something you feel. Imagine leaving Earth and accelerating steadily. Planets slide behind you. The sun shrinks to a bright star. The entire solar system becomes a memory, and then nothing happens for years. Then decades, then generations, because between stars there is mostly emptiness. And the unsettling part is that even light, which outruns everything, still needs over 4 years to make the crossing which means every slower object is automatically trapped in time scales that stop feeling human. What changes it for 24 light years is not just distance, but the meaning of distance, because inside the solar system you can imagine rescue, repair, communication, return, but beyond it you begin to lose those assumptions one by one. Messages take years. Help is impossible. And the act of traveling becomes a commitment measured not in missions but in eras. The number itself does not frighten you at first, because 24 looks harmless, almost precise. But the moment you translate it into time, into motion, into the limits of machines, you realize the nearest star is not simply farther away than anything we have reached. It exists on a scale where everything we have ever done in space shrinks into a small prelude, and the comforting idea that Proxima Centauri is close begins to dissolve, replaced by the quiet recognition that the nearest destination beyond our sun is separated from us not just by distance, but by a gulf so vast that even our fastest achievements barely register against it. Once you accept the distance, your instinct immediately shifts to speed, because distance only matters if you cannot cross it fast enough. And that is where propulsion enters the conversation, and where things quietly become more uncomfortable, because everything we have ever used to move through space relies on the same simple idea. You throw mass backward and you move forward. A direct consequence of Newton's third law, elegant and reliable. And it has carried us from Earth to the moon, past Jupiter, out beyond the edge of the solar system. So it feels natural to assume that faster rockets are simply the next step. But the mathematics hiding underneath that intuition are not linear. They are exponential. And exponential growth has a way of turning reasonable expectations into physical impossibilities. The kinetic energy of a spacecraft increases with the square of its velocity, which means doubling your speed requires 4 times the energy. Tripling it requires 9 times the energy. And once you start talking about interstellar travel, you are not doubling or tripling. You are increasing speed by factors of thousands compared to what we currently achieve, and suddenly the numbers explode. Voyager 1 moves at about 17 kilometers per second. But reaching even 10% of the speed of light requires about 30 kilometers per second, roughly 700 times faster. And when you square that factor, the energy requirement becomes nearly 3 million times larger, which is already unsettling. But the real problem is not just the energy you need to move the ship. It is the fuel you must carry to produce that energy. The rocket equation, derived in the late 19th century, describes this relationship, and it contains an exponential term that punishes ambition. Because every kilogram of fuel you add increases the mass, you must accelerate, which requires more fuel, which increases the mass again. And the cycle spirals, and this is not a technological limitation that clever engineering can sidestep. It is embedded in the mathematics of propulsion itself. Chemical rockets, the workhorses of spaceflight, have exhaust velocities of a few kilometers per second, which is perfectly adequate for escaping Earth or navigating the solar system, but hopeless for interstellar travel, because the fuel required to reach even a few percent of light speed would exceed the mass of planets. Not metaphorically, but literally. And you can try to improve efficiency with electric propulsion. Ion engines that accelerate particles to higher velocities, and those engines are indeed more efficient, but they produce extremely low thrust, meaning they accelerate spacecraft slowly over months or years. And while that is ideal for deep space missions within the solar system, it collapses when you try to reach interstellar speeds, because the acceleration period stretches into decades or centuries, and the power requirements climb beyond anything a spacecraft could realistically carry. You begin to see that the engines that work beautifully in our neighborhood fail precisely because they are designed for patience, not velocity, and interstellar travel demands both simultaneously. The situation becomes even stranger when you consider the scale of energy required for a human mission. Imagine a vessel massing tens of thousands of tons, modest by the standards of sustaining a crew for decades. Accelerating that mass to 10% of light speed requires kinetic energy comparable to decades of total global energy production. And that is only the energy delivered to the ship itself, not counting inefficiencies, not counting fuel mass, not counting deceleration, which requires roughly the same energy again, and the calculation starts to feel less like engineering and more like accounting for a civilization's entire output. At that point you realize the propulsion crisis is not about building a better rocket. It is about confronting the fact that rockets, as we understand them, may not scale to interstellar distances at all, because the principle that makes them work also makes them fail when pushed too far. And the closer you look, the more the problem tightens. Fuel becomes mass. Mass becomes energy. Energy becomes more fuel. And the system loops back on itself until the numbers no longer represent something you can build, only something you can write down. What makes this unsettling is not that propulsion is difficult, but that the difficulty comes from familiar physics behaving exactly as expected. There is no exotic barrier, no mysterious force stopping you. Just the ordinary rules of motion applied to extraordinary distances, and those rules quietly reveal that the engines which carried us across the solar system do not form a ladder to the stars. They form a ceiling. Once conventional rockets collapse under their own mathematics, the conversation inevitably drifts toward ideas that sound less like engineering and more like controlled explosions. And that shift is not accidental, because if chemical energy is too weak, you reach for the atom. And if the atom is not enough, you reach for annihilation itself. And what emerges is a catalog of propulsion concepts that are physically plausible, yet strangely distant from anything we have ever built. One of the earliest was nuclear pulse propulsion, a proposal so blunt that it almost feels like a joke, instead of burning fuel smoothly. You detonate nuclear bombs behind the spacecraft and ride the shock waves forward, each explosion slamming into a massive pusher plate that absorbs the impulse. And when you first hear it, it sounds reckless. But the physics is surprisingly clean. Nuclear explosions release enormous energy densities, and repeated pulses could in principle accelerate a large vessel to several % of the speed of light, fast enough to reach nearby stars within a century. And yet the moment you imagine the scale, thousands or millions of nuclear detonations, a ship weighing tens of thousands of tons, the engineering shifts from audacious to surreal. And even if you ignore the political impossibility of launching nuclear bombs into space, the concept quietly exposes the magnitude of what interstellar travel demands. Because this is not a refinement of rocketry. It is a redefinition of propulsion as a controlled chain of stellar-scale impulses. Fusion propulsion sounds cleaner, more elegant, harnessing the same process that powers the sun, fusing light nuclei to release energy far greater than fission. And in theory, a fusion drive could accelerate exhaust to tens of thousands of kilometers per second, bringing travel times to decades rather than millennia. But the optimism hides a crucial detail. we have not yet built a fusion reactor that produces sustained net power on Earth, and the versions envisioned for spacecraft are not simply smaller reactors. They must be lighter, more reliable, capable of operating continuously for decades, and able to channel plasma hotter than the core of a star into directed thrust, which transforms the problem from building a power plant into building a controlled star that doubles as an engine. Antimatter propulsion pushes the idea further, because when matter meets antimatter, mass converts entirely into energy, the highest energy density allowed by physics. And in principle, a few hundred kilograms could drive a spacecraft to relativistic speeds, but the difficulty appears immediately when you ask how to obtain that antimatter. Since humanity has produced only microscopic quantities in particle accelerators, and storing even grams requires magnetic traps that prevent contact with normal matter, because touching the container walls would trigger instantaneous annihilation. And the irony is almost uncomfortable. The most efficient fuel in the universe is also the one that refuses to exist in useful amounts, forcing you to imagine industrial-scale antimatter factories, storage systems hovering at the edge of failure, and propulsion that releases energy partly as gamma rays and neutrinos, most of which cannot even be captured for thrust. Then there is a concept that abandons fuel entirely: laser-driven sails, where a ground-based array fires an immense beam at a reflective sail, pushing a tiny spacecraft to a fraction of light speed. And this idea has a certain elegance because it removes the mass of fuel, turning propulsion into a problem of light pressure and materials. Science and in simulations, gram-scale probes could reach Proxima Centauri in a few decades, but the simplicity dissolves once you consider the requirements. A laser array producing power comparable to large national grids, sails only atoms thick yet kilometers wide, navigation at relativistic speed through interstellar dust, communication from a chip, traveling faster than anything ever built, and the design quietly accepts that the probe will never slow down. It will simply rush past the destination, collecting a few hours of data before vanishing into darkness. What unites these ideas is not their optimism, but their scale. Each one abandons conventional engineering and replaces it with something that sounds extreme, because the problem itself is extreme. Nuclear explosions, miniature stars, annihilation engines, light-driven sails, and none of them exist beyond studies. Prototype, or theoretical models, which means the path to another star, is not a continuation of current technology, but a leap into architectures that have never left paper. The uncomfortable realization is that interstellar travel does not merely require better machines. It demands machines so different from what we build today that even our most serious proposals feel like sketches of a future civilization rather than plans for our own. Even if you imagine that propulsion is somehow solved, that a spacecraft can reach a fraction of light speed and cross the distance in decades instead of millennia, another problem quietly takes its place. And this one is not about engines or energy, but about you. Because the moment humans board the ship, the mission stops being a physics experiment and becomes a biological gamble. And biology is far less forgiving than mechanics. Interstellar space is not empty in the comforting sense. It is saturated with galactic cosmic rays. High-energy particles accelerated by supernova explosions and violent astrophysical events across the galaxy. And these particles move at significant fractions of the speed of light, carrying enough energy to punch through spacecraft hulls, through electronics, and through human tissue, leaving trails of ionization that shatter DNA and trigger cascades of cellular damage, On Earth, you are protected by the atmosphere and the planet's magnetic field, which deflect and absorb much of this radiation. But once you leave that shield, the exposure rises dramatically. And in deep space, the dose accumulates slowly but relentlessly, year after year, without interruption, over a multi-decade journey to another star. The total radiation exposure could reach levels associated with dramatically increased cancer risk, neurological damage, and degenerative disease, not as a sudden catastrophe, but as a gradual erosion of health, the kind that unfolds silently, cell by cell, until the body begins to fail in ways that no onboard medical system can fully repair. Shielding seems like the obvious solution, but high-energy cosmic rays behave differently from the radiation you encounter in medical imaging. Dense materials, such as lead, can actually worsen the problem by producing showers of secondary particles when struck, and the more effective shielding involves hydrogen-rich materials like water, which means surrounding the habitat with layers tens of centimeters thick, translating into hundreds of tons of mass. And every ton added to protect the crew makes the propulsion challenge heavier. Turning survival into a trade-off between biology and physics, even if radiation were somehow managed, the spacecraft must function as a completely closed ecosystem because there is no resupply. No cargo ship arriving with spare filters or fresh food. And this requirement sounds straightforward until you realize that no human system has ever achieved perfect closure. The International Space Station recycles water and air, but it depends on frequent deliveries from Earth. And when engineers attempted to build a sealed ecological habitat on Earth itself, Biosphere 2, the experiment struggled with falling oxygen levels, unstable carbon dioxide, crop failures, and unexpected ecological imbalances, and that was under sunlight, gravity, and the ability to intervene, whereas an interstellar vessel must maintain stability for decades in isolation. Food production becomes a continuous experiment with no margin for failure. Crops must grow reliably. Nutrients must cycle without loss. Microorganisms must remain balanced. And one prolonged disruption does not mean inconvenience. It means starvation slowly tightening its grip across a confined population. Water recycling, oxygen regeneration, waste processing, temperature control, and atmospheric balance must all operate in closed loops, and every loop must function without degradation. Yet all mechanical systems wear down, seals crack, filters clog, sensors drift, and in deep space there is no warehouse of replacement parts, only what you carried at launch and whatever improvisation the crew can manage. Medicine introduces another layer of fragility because injuries, affection, and chronic diseases do not pause for exploration. And a small medical team must handle everything from fractures to surgery without evacuation, without specialized hospitals, and without resupply of pharmaceuticals, while the same radiation that threatens the crew also degrades immune function, increasing vulnerability to disease. The unsettling truth is that a robotic probe does not eat, does not age, does not develop cancer, does not require oxygen or psychological resilience. And once you place humans aboard, every one of those needs becomes a continuous demand on a system that cannot fail even once. Because failure in interstellar space is not dramatic. It is gradual, a drop in oxygen efficiency, a crop yield declining year by year, a medical condition that cannot be treated, and the ship does not explode. It slowly stops being a place where humans can live, revealing that the hardest part of reaching another star may not be getting there, but remaining alive long enough to see it, long before the ship reaches another star. Something subtler begins to change, and it has nothing to do with engines or radiation or life support chemistry. It has to do with what happens to people when distance becomes permanent, because inside the solar system you are never truly alone. Signals return within minutes or hours. Mission control answers. Rescue remains theoretically possible, and even when you are millions of kilometers from Earth, there is still a psychological thread connecting you to home. But once you commit to a multi-decade interstellar mission, that thread stretches until it becomes something abstract. Messages take years. Replies take years more. And conversations dissolve into historical artifacts rather than communication. You speak to people who no longer exist in the same present as you. And over time, the idea of Earth shifts from a place you belong to into something like a memory that continues without you. Isolation in space has been studied in fragments, Antarctic stations, submarines, seal habitat experiments, and every one of them reveals the same pattern. Small groups confined for long durations begin to change. Sleep cycles drift, motivation fluctuates, minor disagreements accumulate weight, personalities that once complemented each other begin to grind, and these effects appear even when participants know the mission will end, that they will return to normal life, that they can eventually leave, but an interstellar mission removes that escape valve entirely. The crew departs, knowing there is no return for decades, possibly no return at all, and that knowledge alters every interaction, because conflicts cannot be walked away from. Authority cannot be replaced by outside arbitration. And dissatisfaction has nowhere to go except inward. Governance becomes more than a procedural detail. It becomes a survival mechanism, and any structure, hierarchical command, democratic decision-making. Hybrid systems carries risks amplified by confinement. And a rigid hierarchy may maintain efficiency, but risks resentment that grows silently over years, while a democratic model invites factionalism in a population too small to absorb division, and once disagreements extend into resource allocation, work assignments, or reproduction policy, they stop being philosophical and become existential, because every decision touches survival. Over time, the mission's original purpose may begin to erode. The founding crew volunteered. They believed in the journey. But decades later, new members, perhaps children born aboard, inherit a destination they did not choose. A life inside a vessel they cannot leave. And the psychological weight of obligation replaces the enthusiasm of exploration, turning duty into something closer to necessity. Meanwhile, the systems keeping everyone alive continue aging. Pumps vibrate, seals degrade, electronics accumulate radiation damage, and repairs become routine, then constant, then exhausting, and the crew must balance technical maintenance with emotional endurance, because a failing system is not just a mechanical issue. It is a reminder that survival depends on machines that cannot be replaced. The ship becomes a closed world where every failure has social consequences. A malfunction in water recycling demands rationing. Rationing breeds tension. Tension magnifies conflict, and conflict distracts from maintenance, feeding a cycle that is as much psychological as technical. Communication delays deepen the isolation. Advice from Earth arrives years late. Condolences arrive after grief has already passed. Celebrations echo into a future that no longer aligns. And slowly the crew becomes culturally detached, evolving its own norm, priorities, and identity. until Earth feels less like home and more like a distant origin story. In such an environment, cohesion is not guaranteed by training or discipline. It must be rebuilt continuously. Negotiated through routine, shared purpose, and the fragile understanding that survival depends on cooperation, yet human history shows how fragile that balance can be even under far less extreme conditions. What makes this unsettling is that nothing dramatic needs to happen for collapse to begin. No explosion, no catastrophic failure, only fatigue, disagreement, and the slow realization that the mission extends beyond any individual lifetime. And as that realization settles in, the ship transforms from a vehicle into a permanent society, one that must remain stable, not for months or years, but for decades, with no external support and no margin for fragmentation. And the quiet pressure of that permanence begins to weigh on every conversation, every decision, every moment of silence. After decades of travel, after engines have burned, systems have held together, and a small society has endured the long quiet between stars, the destination finally begins to grow brighter ahead. And it is tempting to imagine this moment as the end of the journey. But in physics, arrival is not defined by proximity. It is defined by velocity, and a spacecraft moving at a significant fraction of the speed of light does not arrive simply because it reaches the right location. It passes through, and the difference between those two outcomes is enormous. At 10% of light speed, a common optimistic target for interstellar travel, the ship is moving at roughly 30,000 kilometers per second, which means the entire region around Proxima Centauri, including the orbit of Proxima b, would sweep past in hours or days at most. And without deceleration, the destination becomes nothing more than a fleeting glimpse, a brief window of observation, followed by permanent departure into deeper interstellar space. This is the part that intuition resists, because we instinctively think of reaching a place as the hardest step. Yet in interstellar travel, slowing down may demand as much energy as speeding up. And if propulsion required enormous fuel reserves for acceleration, deceleration doubles the burden, forcing the ship to carry fuel not only for the journey outward, but for the act of stopping. And every kilogram of braking fuel had to be accelerated for decades beforehand, compounding the mass and energy requirements exponentially. Alternative braking concepts exist. Magnetic sails interacting with the interstellar medium, photon pressure from the destination star, or other speculative methods, but each one operates under severe constraints. The interstellar medium is thin, producing extremely gentle drag, which means deceleration could take years. And during that time, the ship must maintain precise orientation and structural integrity after decades of wear, while photon braking depends on stellar luminosity, and Proxima Centauri is a dim red dwarf emitting only a fraction of the sun's light, far too weak to meaningfully slow a large vessel. Even if braking systems function perfectly, the environment during arrival introduces another layer of risk, because at relativistic speeds, tiny particles of interstellar dust carry significant kinetic energy. And over decades, the ship's forward shielding absorbs continuous impacts, gradually eroding protective layers. So by the time deceleration begins, surfaces may already be degraded, and reorienting the ship to fire engines or deploy braking systems exposes new areas to potential damage, turning arrival into a delicate choreography between momentum, shielding, and mechanical reliability. Suppose the ship manages all of this. Velocity drops, Proxima Centauri becomes a star. You can orbit rather than a blur you rush past. And attention shifts to the planet that justified the entire mission. Yet here another uncertainty emerges. Because Proxima b exists within the habitable zone, but that term only describes temperature ranges compatible with liquid water, not the presence of oceans. Atmosphere, or life. Proxima Centauri is an active flare star, releasing bursts of radiation that could strip atmospheres over time. And if the planet lacks a strong magnetic field, it may have been eroded into a barren rock, tidally locked with one side permanently facing the star, the other locked in darkness, and the narrow region between them, possibly the only place with moderate conditions. If any atmosphere remains at all, the crew that crossed interstellar space may discover not a second Earth but a silent world, scorched, frozen, or hostile, in ways that no preparation can fix. And because communication delays stretch to years, the realization unfolds in isolation, far from any possibility of reconsideration or retreat. What makes this unsettling is that arrival does not resolve the mission. It reveals its final uncertainty, because the entire undertaking depends on conditions that cannot be confirmed until the journey is complete. And the ship that finally slows into orbit carries not only the weight of decades, but the possibility that the nearest habitable candidate is not habitable at all, leaving the crew suspended between accomplishment and ambiguity, having crossed the gulf only to confront the quiet recognition that distance was never the only barrier, and that reaching another star does not guarantee finding a place where humans can remain